All right, welcome back everybody. In this video we're going to talk about information related to section 8.5 of AP Calculus, finding the area between curves expressed as functions of y. And really the whole kind of idea for us here is pretty much identical to what it was when we were talking about finding the area between curves expressed as functions of x. The only difference is now we want everything to be in terms of y in our integrand. And instead of looking at, an upper curve and a lower curve, we're looking for a rightmost curve. That's the curve that's going to be first in your integrand, and a leftmost curve. And honestly, people have more trouble producing the graphs for these. Largely, I think, my theory is that we've grown so dependent on our graphing calculators over the years. So we're going to do two examples hopefully in this lesson. Example 1, we're going to go ahead and do this all by hand. And then in example 2, I'm going to try and show you a little cheat code as far as how we can handle some of these problems when we're finding area between curves expressed as functions of y. All right, so the first thing I'm going to do in this particular problem is I'm going to go ahead and graph my two curves. And so I'm going to start with a Cartesian coordinate. I think that -5 to 5 will be sufficient for us here. All right, so first I'm going to graph x equals y squared plus 2y minus 3, and all I'm going to do is pick some y values and substitute them in and find the value of x that goes with them. When y is 1, x is 0. So we've got that point right there. When y is 0, x is -3. When y is -1, x is 1 minus 2 minus 3 is -4. When x is -2, oh, there we go. There's my parabola. And I can see the parabola forming. And there we go. There's the graph of y squared, x equals y squared plus 2y minus 3. Okay. And then x equals 2y plus 1. So let's see, when y is 0, x is 1. And this is just going to have a slope of 1/2. So can go ahead and plot points, and it's going to hit that point there. It's going to hit that point there. And there's my line. And so I'm looking for the area of this region right here. Now, when we're talking about finding areas with respect to y, I mentioned before, instead of thinking about upper curve, lower curve, this way is up when we talk about x. And so the curve that's further to the right is going to be my upper boundary. So when I set up this integral, the first curve is going to be the line. That's going to be my upper boundary, and it's in there in terms of y. And then my parabola is going to be my quote-unquote lower boundary of this region. And that's going to be my second curve. And now I need the limits of integration. And I'm going to use endpoints of this integral. Now, if you remember when we were integrating functions expressed in terms of x, we went from the left-hand side of the region to the right-hand side of the region. When we're finding areas of functions expressed in terms of y, instead of going from left to right, we're going to go from bottom to top of the region. Okay? And these limits of integration are going to be y coordinates. So first off, I want the y coordinate of the point of intersection that's at the bottom of the region. That's -2. And then I want the y coordinate of the point that's at the top of the region. That's +2. And there's my setup. And now I can go ahead and integrate this, since I did this all by hand so far. Don't stop now. I'm going to go ahead and simplify this. 2y minus 2y, those cancel out. 1 minus -3. There's my integral. I'm going to go ahead and find my antiderivative and evaluate this from -2 to 2. And then I'm going to go ahead and substitute. -1/3 times 2 cubed plus 4 times 2 minus -1/3 times -2 cubed plus 4 times -2, which becomes, let's see, -8/3 plus 8 minus 8/3 minus 8. So that's 16 minus 16/3. That ends up being 32/3 for our area between those two curves. All right. Example 2. Find the area of the region bounded by x equals sine of y and x equals y squared minus 1. Now this one's going to be a little bit tougher for me. I know that this is a parabola, x equals y squared minus 1. I'm pretty good with what that looks like. X equals y squared minus 1 is going to look like this. And then I've got x equals sine of y, which is going to be a sine curve going through here. That's a really terrible picture. But I'm roughly looking at a region like this. Okay? And from all of that, I can tell that my upper curve, or my right curve for this region, is the sine curve. So that's going to come first in our integrand. And my leftmost curve is the parabola. So I've got that all set up. Now I need these limits of integration, and I need the y coordinates of these limits of integration. So I can do this in a couple of ways. I could set this these two equal to one another and try and solve that equation for y. But the little trick that I've used for a long time when doing problems like this is, instead of trying to find the area of this region, what I do is I graph the inverse of this region and find the area and find the information by using the inverse of this region. Okay, so let's show you what I mean by this. I'm going to go ahead and graph the inverse of x equals sine of y, which is y equals sine of x. Well, actually, before I do that, let's talk about how I could do this without doing the inverses. I could solve both of these equations for y. This is y equals arc sine of x, and this is y equals plus or minus the square root of x plus 1. And I could go ahead and graph those. Let's see, I've got to do two different graphs for the plus or minus. Okay, and oops, I want to zoom to a standard window. Now, one of the problems with this is I don't know that the arcsine function is going to give me everything that I need here. Well, maybe it will give me just enough. Okay, let's zoom in on this. There's my arcsine function. It gives me a piece. Does it give me enough? Looks like it just might. Just barely. Let's see if we can find these limits of integration. You see my region's a little bit off when I graphed it, but let's find these intersections. So the first curve is the arcsine, second curve is this branch. And let's see if it'll give me this intersection point. I think I might just have enough, just barely. Maybe not. Oh no, it didn't find a solution. Oh my goodness, there it is. So unfortunately, I can't get the intersection point from here. Let me see. Let me try that one more time. Maybe I just didn't go far enough. See, yeah, it's going to go off. Yeah, just not going to get a solution. Gosh, this is a problem. So what can I do? What I can do is what I was just talking about a few moments ago. I can graph the inverses of these functions instead. And instead of graphing, I'll graph y equals the sine of x. And I'll graph y equals x squared minus 1. And when I do that, the graph I get is the inverse of the graph that I see here, which means it's flipped over the line y equals x. But you'll notice y equals sine of x is the upper curve, just like x equals sine of y is our rightmost curve. Y equals x squared minus 1 is our lower curve here, just like it's the leftmost curve here. And these points of intersection are going to have the same coordinates as these points of intersection, except that those coordinates will be flipped. So let me go ahead and find these intersection points on this graph. And that means that the intersection points on this graph are flipped from those. So instead of being this, the coordinates of this are negative 0.594, 5715, comma, negative 0.636, 7327. Let's get the other intersection point a while. The coordinates of this are similarly flipped, so they're going to be 0.987, 03983, comma, 1.409624. Now, in reality, I want the y coordinates of these points as my limits of integration. So since I took the inverse when I graphed this, I actually want the x coordinates from my calculator as my limits of integration. But we'll put these in, and that enables us to get around the fact that I couldn't get that intersection point because of the limits on the domain and range of the arcsine function. And now I can go ahead and calculate this integral. So I've got sine of y minus the quantity y squared minus 1 with respect to y from negative 0.6367327 to 1.409624. Oops. And I get 1.670 for the area. And that's how I can use inverses to help me when I've got curves as functions with respect to y, and I'm trying to find the area of them on my calculator. A little cheat code that you can use to help you find these when it's otherwise pretty difficult. Alright, that takes us to the end of this video. We're going to come back next time and do a little bit more with this topic, and I'll see you then. Have a great rest of your day. Bye-bye now.